Here we go. We're on to Unit 4, Waves and Simple Harmonic Motion. And before you do Lesson 43, you should go onto YouTube and watch this video, Simple Harmonic Motion, Crash Course Physics number 16. All right, so pause the video here, watch that video. It'll give you a great introduction to this unit, and it will make everything that I'm going to talk about here make a lot more sense. So before we just get onto all of this, let's just talk about simple harmonic motion, which is very simply a motion that repeats over and over again in the same time period. So for example, if you have a spring like that one there, and then you stretch that spring and then release it, what's it going to do? It's going to oscillate back and forth like this. Now it's going to oscillate. This is going to be called the equilibrium point. So at this point here, where the spring is just sitting all willy-nilly, doing nothing, it's stationary, it's at its equilibrium. When you stretch it, there is all of a sudden a restoring force. It wants to go back this way, and it wants to get to its equilibrium. But because it's a spring, it's going to, once it starts going this way, it's going to overshoot its equilibrium point right here, and then it's going to become really compressed, and then it's going to want to restore in this direction. Fs. Fs stands for the restoring force, and we've talked about that a little bit in the previous unit. So what's it going to do? The spring is just going to oscillate back and forth between its equilibrium position. And that's simple harmonic motion. Now, obviously, at some point it's going to stop because of friction and air resistance and stuff like that. But for the purposes of this unit, we will say that this spring is just going to oscillate back and forth in between its equilibrium position. And let's just talk about a couple of the characteristics of that oscillating motion. Number one, it must be in a constant state of acceleration, because you stretch it out. Once you let go of it, it's not moving here. And once you let go of it, it's going to accelerate, accelerate, accelerate. It's going to get to this point here, at which point it will reach its maximum velocity, and then it's going to start slowing down, slowing down, slowing down, and it's going to come to a stop right here. So the velocity here is 0, and the velocity there is also 0. And the velocity maximum is in the midpoints of its oscillation, or its equilibrium position. So the maximum velocity is at its equilibrium position. The maximum acceleration, which this may be a little counterintuitive, is right here. It has the maximum amount of acceleration. So the acceleration is its max on either end. And the acceleration is 0 in the middle. So you can see how the velocity and the acceleration are opposite one another. So those are some characteristics. And the time that it takes to do this oscillation, we know as the period. Capital T means the amount of time. It means period. It's the amount of time for something to complete something. The period of Earth's rotation is 24 hours. The period of Earth's revolution is 365 days. The period of an oscillating spring is maybe 2 seconds or whatever it is. And pendulums follow the same kind of pattern, this pattern of simple harmonic motion, as long as the angle is relatively small. And we'll get more onto that later. Okay, so there's some fundamentals of simple harmonic motion, and then here's your notes. Talks about simple harmonic motion, simple harmonic oscillators. You can read over that. And then we are introduced once again to Hooke's law. Hooke's law right here. Hooke's law says Fs, which is the restoring force, equals negative Kx. And K is the constant of the spring, and that spring constant is different for every spring. If you have a really stiff spring, it has a high K value. If you have a slinky, would have a very low K value. And the X is the distance or the displacement, the amount that you stretch the spring or compress the spring. So example number one is we don't do much vertical stuff, but example number one is a good way to start. It says we have a spring is attached to the ceiling dangling down. So the ceiling is a spring, and it's just hanging there to make a basic scale for measuring masses. The spring has a constant, K value is 38.9 newtons per meter. At first, it is just hanging there on its own at its equilibrium. So right there, it's at its equilibrium point. If a 1.3 kilogram mass is hung from the spring, determine how far it will stretch. So then we take a mass and we put it on the spring, and what's going to happen? It's going to stretch. It's going to stretch, and then again, it will just be hanging there. So the spring will stretch, and it will just hang there, and so it's not moving at this point. We want to determine how far it will stretch. Well, there are two forces happening at this point. You've always, since the spring is being stretched, you've always got the restoring force wanting to restore the spring to its equilibrium position. And obviously, in this case, since we're dealing with a vertical situation, we have gravity pulling it down. And as usual, we're going to make a net force statement. The net force equals the restoring force plus the force of gravity. But as we said, when it's in this position here, or in both positions, it's just stationary. It is not accelerating, it's not moving. So therefore, the net force is 0. And therefore, we can just say that the restoring force equals the negative of the gravitational force. We know the restoring force is Kx. We know that the force of gravity is mg, so plug those variables in. And the question is asking for how much is the spring stretched. So we're looking for the x value. And you can see the negatives cancel out. So what will we use for the mass here is the 1.3. Stick that into your calculator, and you're going to get an answer of negative 0.33 meters. In other words, 33 centimeters down. Okay, so that's a typical Hooke's law question. Then if you go into your next page, it talks about what I discussed with the restoring force and acceleration, and well, actually it doesn't go into acceleration velocity yet, but it's just talking about this diagram is talking about the direction and the magnitude of the restoring force and the gravitational force in a vertical spring. So you can see that the gravitational vector is always down and it's always the same size. But the restoring force vector changes direction and it changes magnitude. So in B, when you stretch the spring out, it obviously increases the restoring force, and so you have a longer vector. And then in D over here, where the spring is now above the equilibrium position, the restoring force is in a different direction and again has a fairly significant magnitude. Okay, and then we go on to the last concept for this first lesson, and that is pendulums. Pendulums are also an example of simple harmonic motion, although they are not perfect. Pendulums are great though for many physics applications, because the only thing that makes a pendulum move is gravity, and gravity is really constant. And so we can use pendulums in physics a great deal. When a pendulum is just sitting on its own, it has no reason to do anything else, but if you pull it to the side, then again, it has a restoring force. And this diagram here is really important to make sure you look over it carefully. And note the right angle triangle that is created here. We have three forces. You have the perpendicular force, the gravitational force, and the restoring force. Okay, and we'll discuss all that when we do an example. So since the restoring force is not directly related to displacements, we can't say it's simple harmonic motion. But if you're dealing with angles that are up to about 15 degrees, pendulums follow a pattern of simple harmonic motion very exactly. So let's do an example. I think, yes, here we go. We got a 2 kilogram mass attached to the end of the pendulum. If the pendulum is held at a 10-degree angle from the equilibrium, determine the restoring force. So here's the diagram for you. You can see that that's a right angle. And you can see that we are trying to find the restoring force. We don't have the perpendicular force, but we can certainly calculate the force of gravity, because the force of gravity always equals mg. So if I'm trying to find the restoring force and I have the force of gravity, what's the trigonometric relationship that relates all those two? And the answer is sine, because the restoring force is the opposite and the force of gravity is the hypotenuse. So I'm just going to say that the sine of 10 degrees equals the opposite, the restoring force, over the hypotenuse, which is the force of gravity. And I'm solving for Fs here, the restoring force. So that's going to equal sine 10 times m times g. You can put the negative or leave it out. It's irrelevant. We know that the restoring force, the direction of the restoring force is simply back to its equilibrium position. So the negative is doesn't really mean anything in this case. Stick that into your calculator and you are going to get 3.4 newtons. And if you want it to be exact, you would just say 3.4 newtons in the direction of its equilibrium position. Okay, that ends lesson 43. On to lesson 44.